research is about distributed quantum computing using superconducting circuits, meaning that when we want to scale up quantum processors, there might be different ways, and for example, you can have more qubits on a single quantum processor, and there is also another way to have multiple processors distributed and connected together and use that for running a single task. By doing this, you can scale up the processor without having a lot of qubits on each processor. And that's basically what I'm doing. And we use superconducting qubits to build these processors and also build links between these processors. So this frequency-bin paper is one of the results in our project. As what I said before, we build links between quantum processors, and within these links, which is the quantum channel that we called, we use photons to transfer information. So we have a photon generated from the quantum processor traveling through the link and then being reabsorbed by the other quantum processor. By this way, we link them up. You can then see that one of the most important building blocks for such a system is to how to transfer information from the qubit into those photons, and how to reabsorb information from photons to these processors. So our work in this frequency-bin paper is basically the first step, how you encode information from a qubit on a superconducting chip onto these photons. And instead of using photons in a single frequency, we do that by having multiple frequencies. We generate these photons in 2 different frequencies, and it's gonna help with if there's any photon get lost during the transformation inside this channel, it can help us to detect those photon loss. So as what I mentioned, there are many ways to build the channel, and with photons, it could be a single photon in a single frequency, or it could be photons in different frequencies. And for our case, when you have different frequencies, it adds another degree of freedom in this information encoding process. By having this extra degree of freedom, whenever there is an error happens, that will result in a special pattern that is detectable. For our case, it's gonna result in you receive this photon at the receiver's quantum processor. The qubit would be inside a flag state instead of the right encoding subspace. So by detecting that using a quantum non-demolition measurement, which is a specific type of measurement, we can detect the photon loss and resend the photon. That helps with solving the lossy channel problem in a distributed quantum computing setup. I think for our case, we not only want to do this frequency-bin encoding, but we also want to do it with a hardware efficient way, meaning that we want to use as little amount of qubits as possible. So usually when it comes to frequency-bin, we would need multiple modes. So we would need a lot more qubits than a single photon solution. But in our case, we reduced the number of qubits needed by having some simultaneous drives and also by bringing several components on resonance to form this hybridized mode that both are coupled to the waveguide. So this is novel and is hardware efficient, but also at the beginning we don't know, since it haven't been done before, we don't know if there are crosstalks between these simultaneous drives and so on. But in the end, it all turned out to be, there's no problem and in the experiment, and it turned out to be nice. It's a very big question. I think this field of distributed quantum computing, it gives us a way as a heralding protocol to overcome this error, the photon loss problem. And in a more general perspective, it offers a way to scale up quantum computers, and hopefully, like all these different methods, we can use them in a hybridized way and scale up the quantum processors and make it more useful in the future.